Okay, I was a co-organizer of this focus section, so I played the trick. I'm the last one, so I can talk for 20 minutes, right? Don't worry about your dinner. Don't worry about your dinner. So don't worry, actually, I just have probably a handful of slides that are important. The rest are just informational. So when I hit the important one, maybe I can just wake you up and say, hey, pay attention. Yeah. So it's a very large subject. 12 minutes really doesn't do justice whatsoever, but I'm going to try. So in any event, we worry about the strength of our rubber, and according to the tradition, I have a flipper. We actually follow fracture mechanics. We think your rubber is weak because there are flaws in the problem. And if there is flaws, there is a way I can determine what is my strength by so-called measuring the toughness by making a pre-cut. So we have started to look at this problem by realizing, gee, maybe I can really determine my strength is really nominal, as I measured at the top, or it is something much higher. So imagine, what if I can determine the stress upon fracture at the crack tip? We learned a lot. There are a bunch of papers already. And the things, this is an important slide. I should spend time, but there's no time, right? So it turns out we learned a great deal in terms of connecting what determines the toughness magnitude. It's determined by the strength of your material. Okay, that's enough. So let's move on. There's a movie I'm not even going to show you. So basically, we did birefringence, and we can indeed claim to be able to determine the stress. So at the end of the day, this essence of elastomeric fracture is really about talking about rate and temperature dependence of the strength and toughness. There are old topics, textbooks written. These are classical papers based on which the textbooks are written. Let me review for you what they did. This is all in the 50s done, okay? Older than me. So basically, you take a rubber. It doesn't matter you use this faster stretching, you draw faster, or you go to lower temperature. This is a bunch of curves. The point is, if you draw faster, you go to lower temperature, you stretch more. You can stretch more. And the toughness I so briefly defined, somewhat resistant to fracture, is also doing the same. If you use higher rate of stretch, it grows. If you go to lower temperature, it's higher. Okay? And these guys, they worked on this for 70 years to show the feature that I just showed you. Textbook conclusions are, this is a matter of polymer viscoelasticity. And we already published a paper to show that there is a different way to think about it. Let's go back to 50s. These are the two curves. Take your rubber, draw it at 3 different rates. Higher rate, the more you draw. Take the two temperatures, right? One is high, you draw very little before it breaks. And when it's lower temperature, you draw more. Okay. Same curve again. You know what they did? That's the invention of WF at the time. Let me shift. Create a master curve. Okay? And you do this for a bunch of curves. And you can even see, oh, that's WF-like. Conclusion? This problem is a viscoelasticity problem. That just speaks against common sense. Because it's an elastomer. It should break chains. Breaking chains should come into the story. So the next, how much time I have? The next 5 minutes, I will spend most of my time talking about my theory, and very little time talking about the data, which involves 3 different systems. Let's go back. A coil has so little tension as I stretch. Even by the time I stretch straight, it's only 4 piconewton. The bond lifetime is beyond age of the universe. Stretch more. By the time you stretch about 3 nanonewton or so, you realize the bond lifetime crashes down like mad. This is a density functional calculation. Pay attention to just this region. That is experimentally relevant. 100 days, do you have 100 days? And a millisecond. Just this range dictates what bond tension would be relevant to our experiment. The whole story, as I showed you here, is that depending on the tension there, it regulates what lifetime you have. So the rest of the whole thing is about describing what this theory does to help us. And the next slide is informational, so you can fall asleep if you don't care about information. Basically, it's about determining this activation energy with respect to the bond tension. So I will be very fast, okay? So basically, there's this without force is the red. When you put a certain amount of force, boom, the barrier drops, and it drops so much. And then the barrier is related explicitly, analytically, to the bond tension, okay? That's here, okay, done. And we are going to focus, as I told you, just around this region that's experimentally relevant. So everything is about certain force and certain bond lifetime. So if you use maximum force, then of course there's no barrier, which means it occurs instantly. Now I'm going to patiently tell you what I think happened in your dear elastomers. It's something like this, right? As you draw, some bond reaches 4 nanonewtons already, but the rest hasn't. Draw more. Whoops, you got one. And then this is my microscopic SS curve, right? Sorry, I get excited all the time. So then there's the next one, and you draw next. Boom, there will be next one. So you patiently will see, oh, that's how I build the stress. And all the bonds start to build and sit at this 4 nanonewton. So instead of the blue curve, where the force diverges as I reach full extension with respect to my chain stretching, my elastomer is building chain tension here with respect to my rubber stretching ratio in this manner. This is a big guess that I'm using this reason that they should look like this. Instead of diverging, it's saturating toward that. At the end of the day, if you read what kind of force is in the tension corresponding to how much you stretch, you can have a sense of what the bond lifetime is, because reading the force gives you the bond lifetime. So on the separately, when you stretch, time elapse, you spend time doing it. It's a matter of drawing how much time it takes versus what's the bond lifetime. The whole secret is this bond lifetime matches the time you spend stretching. And this just shows once you have that, basically you solve numerically this solution. This is a nonlinear equation, but you can solve it. Once you solve it by equating them, you find a particular F point which corresponds to a particular amount of rubber stretching, which also correspond, of course, back to what's the bond. Here's the theory. My God, after 35 years of my career, I have, for the first time, able to produce a curve. 35 years. In the past, I just wave my hands, you guys better believe me, and all that kind of thing. This is real. This is my model showing these 3 curves. Does that look like the middle one? So I can collapse too, right? I can just shift my black to the right and red to the left, whatever. I get that curve. The rest, I don't have time. So it turns out that this shift has a lot of deeper meanings about it. But it's certainly not polymer viscoelasticity. It has nothing to do with WF. Sorry, the rest, can we take, we're done. So the rest are 3 systems. I'm going to spend half a minute on each. These are 3 systems. The first one, we are basically commemorating at 3M. So this is a 3M sample. And we show that this is a nice, the reason we choose this nice sample, to your question, repeat many times, it's the same thing. So This was my student, draw them, line them at the same time, you can watch, and then they all break about the same place, stretching to this level. There's indeed a rate dependence. And my theory will be able to capture the feature that it is rate dependent. The higher the rate you use, the more it can stretch. That's first example. Second example, temperature. Remember, the temperature is the thermal energy available to activate. So the temperature, the lower the temperature you go, room temperature being lowest for this PMA, the more you stretch. The higher temperature, the less it stretch. And you plot this, solve this, again, look like it captures the feature that the thing goes. So I'm almost done. So the third one is the most intriguing. In fact, I will probably agitate most of people on this topic. Hydrogel. I had a feeling that this theory would even, I predict, if you change the water in your hydrogel with glycerol, whose viscosity is a factor of 1,000 times larger, this hydrogel will instantly become tougher. So I don't have time to wait. That's the compression result, and turns out it's indeed much more improved just by exchange. So it's already the same sample, right? Structure is already down, everything's down, boom, boom, it's just exchange. And then the next point is of course, you can do a theory, say, oh my God, if I stretch it, should stretch more when I change water to glycerol, right? By glycerol. Here's the story, very fascinating to me. This is a double network. The red is the network with water made in it. Very weak. Upon exchange to glycerol, my only interpretation I can have, the volume is on from the machine, I'm sorry. The only interpretation I could have is this glycerol made the first sacrificial network strong enough, it doesn't collapse. That's the only thing I can do. That's it, I'm done. So, after 35 years, I have a theory. I'm a theorist now, officially. You know, for people who know me, I never divide theory and experiment. It's only one. Yeah. So basically, it's really this mysterious WS-like shift is traced back to the kinetic origin, of the bond dissociation. Believe me now. So we find the theory can really capture all the features of all kinds of systems. Thank you.